Hi, I'm Cmpe492. I'm a student computer engineering department in Bosch University. In this video, I'll mention about my senior project or Cmpe492 project. My project topic is a gate-level event-driven simulation using GPGPUs with Cuda. So, what is it all about? In digital design, more than half of the effort in the design phase goes to verification and validation of the design. In some of those design phases, we have extensive tool support for verification and validation. But in functional verification, our main toolset is simulation. So what is simulation then? Simulation is getting the inputs, processing the inputs, and getting the outputs. So it's basically the same of the actual run of the program. So what is the difference? The difference is you create the inputs such that when you see the outputs, you verify that this digital design works as intended. And let's dive deeper about simulation. We have mainly three types of simulation. First of all, we have a straightforward one. What is it all about? If you're writing a simulator, you get a circuit, you know gates and nets, and you simulate all of them in each time step with a sequential manner. Second one is parallel. In parallel, you know that some of the circuit parts can run in parallel, so you want to gain advantage of it. In event-driven one, you only simulate what you needed. So if there is some parts of the circuit that's never executed, that's never run, then you don't need to simulate those. For example, let's see our simple circuit. You know there is 3 and 2 OR and 1 NOT gate. In our very first approach, straightforward approach, you simulate all of them in a sequential manner. But you know that those AND gates can be simulated in parallel if their inputs are changed at the same time. There is no interaction of those, and there will be no impact if they're simulated in parallel. In event-driven one, it's getting a bit weird. Actually, it's getting a bit wise. For example, let's investigate AND1 gate. Let's say that our AND1 gate's inputs are at this timestamp is 1 and 0, and clearly its output is 0. At the next timestamp, the 1 input changed to 0. In event-driven simulation, you simulate the gate and see that the output doesn't change. So why should I simulate the OR1 gate at the next timestamp? I don't need that. The simulation ends here. And in my project, while I'm parallelization of this simulation, I use Cuda. So why Cuda? Cuda is easy to learn. It's some C with some GPU related calls like device, host, global, Cuda memcopy, Cuda malloc. It's easily wrappable for C++, so you don't need to write anything again in C. You can use your existing C++ code. You just need to write some wrapper functions, and you call Cuda functions in it. But on the other hand, it's quite architecture dependent. So you should know about the architecture of your GPU to get better performances. And also, it's for only NVIDIA GPUs. One of the major things in our design is to consider host device distance, or CPU-GPU distance. As you know, CPU-GPU communicates using a bus, and this bus creates a delay. In my work, my contributions are such that I create a circuit generator that gives me randomly generated circuits, a run generator which creates input vectors for my simulator, For comparison reasons, I first developed Enigma model, which is a sequential event-driven service simulator written in C++. And for my project goal, I created codename Meepo, which is a parallel event-driven service simulator. With the help of Cuda, I parallelized it. And both Enigma and Meepo work same. It has two major parts, an event processor and gate processor. What is done in simulation is you first get input vectors, and input vectors means that, hey, this is the new input for this timestamp, and then you create events for that. Events represent the net changes. An event processor processes those events and says that, oh, this net is changed, so this fan out gate must be simulated. So it creates a gate queue and populates it. Then it passes the gate processor, and gate processor, as you may guess, process those gates and say that, oh, this gate's output has changed, so I should change that net's value, and I should create more events and fill the event queue. And it goes like that. It's a quite simple loop. For Enigma, sequential version, event processor and gate processor sequential code blocks, and for Meepo model or parallel model, event processor and gate processor are parallelized using Cuda. And what's the results? I have up to 6 times speed up for 30,000 gates. It's quite a speed up. For smaller gates, I got at least 2 times faster for my parallel version. Thanks for watching. If you have any questions about the project or are interested in the subject in general, feel free to contact me via setkin.savaşçı@gmail.com.